Welcome to Lab 5, Magnetic Braking with Faraday's Law. The purpose of this lab was to conduct observational data when dropping a magnet through a conductive copper tube, modeling the system, which comprises of the magnet and the tube, on a glow script, and comparing observed data with computational calculations. A little sneak peek of the results are that our average experimental time was 13.73 seconds, which is a lot longer than the computer predicted, which indicates that maybe there was an issue calculating mu in the past lab 4. So some fundamental principles are Faraday's law, which you can see here. Basically, a big part of this is we're eventually going to model this n to be like the length of the tube. So this n is the number of coils. Basically, it's just stating the changing magnetic field through closed loop creates a voltage proportional to the rate of change of the magnetic flux. And then the Biot-Savart law is this formula here. It basically just says a steady current produces a magnetic field around it. The magnitude of the field depends on the magnitude of the current and the distance from the current. And then we also use Newton's third law. Every force has an equal and opposite reaction, and Newton's second law, which is F net equals mass times acceleration. So the procedure was pretty simple. Just drop a magnet of known mass through a copper tube of known length and record the amount of time that it takes for the magnet to fall at the bottom. The magnet was an appropriate width so that it didn't scrape the sides of the copper tube. It was free falling. So really the only thing breaking it, we're going to assume that there's no air resistance, is the magnetic field. We also assume that the bar magnet is a magnetic dipole and that only magnetic and gravitational forces are acting on the system, which is only comprised of the magnet and the tube. So you can see our experimental data here. We ran 3 trials and had pretty similar results for the 3 of them. Some of this data was given to us and other things we found in the past lab, so this is especially important. This mu here, we got 2.149 from the past lab. And yeah, our average experimental time ended up being 13.73 seconds. So let's just get into the code. This was to find the magnetic field. This code was copied from lab 4. And this was to calculate the magnetic flux, which is new to this lab and not relevant for the past one. Yeah. So this section is basically just going through all of the small rings of current and integrating them. So obviously the metal tube isn't necessarily like comprised of rings, but for ease of calculation, we're just modeling it that way so that we can very easily add up all these things together and get the magnetic force created by the whole thing. Yes, and this section was just using principles from Physics 1 and just like stepping through different values to find the position and the velocity, just velocity and position update formulas from Physics 1, and just using F net equals F grad plus F magnetic. So our results were, you can see right here, that the computational time was 3.527 seconds, which is, sorry, I forgot to write the S there, which is probably because the mu is too small. So a smaller dipole moment means that there's less interaction with the magnetic field, which means faster free fall. And the free fall in real time was much longer than predicted, so that basically indicates that our mu calculated in lab 4 was too small, and that there's actually like stronger forces acting through the tube that's slowing it down even more. Some other sources of error other than potentially bad results from lab 4 was that there could have been error recording the time to fall, because just doing it based on eyeing the thing. And then we're not calculating air resistance, but the experiment was not performed in a vacuum, so that's an oversimplification. So just 2 questions to answer. What if the resistivity of the conductor was reduced as close as possible to 0? How would that change the falling magnet? So here, I just like to think about it mathematically. So V equals IR. If the resistance R is decreased, then the induced current I must increase, producing a stronger magnetic field that would slow down the magnet in its free fall. So resistance is reduced as close as possible to 0, we slow the magnet down. And then what if there are holes or slots cut into the tube? For this, we're going to refer back to the Faraday's law formula that we had started with. Basically, if there's holes or slots, we're using less values of n. And if n is decreased, when the pieces of the tube are deleted, then E will be lower, the magnetic field will be lesser, so there's less force acting to slow the magnet down, and therefore it will free fall faster. Thank you for watching.